Well, welcome to our polar area finale, and the good news is I don't think we're going to do anything like that's significantly harder than what we did last night. We're just going to get a little more practice, and as you can see with our first example, we've added a few extra pieces to it. There's a few extra parts, and let's go ahead and we'll jump right in here. They want us to sketch the curve r equals, oh boy, my pen, 1 minus 2 sine of theta. So there's a limicon with an inner loop over the interval from pi over 2 to 3 pi over 2. Kind of a strange interval. So they don't want us to sketch the whole curve. They only want us to do it in certain pieces. And so what we'll do is we're going to attack, let's just get part A out of the way here first of all. And let's see if we can't sketch that curve. Again, I'm going to maybe take a little extra time and do the rectangular version again. See, we know we've got that vertical shift up 1 unit. There's pi over 2, pi, 3 pi over 2, 2 pi. And I'll probably do the rectangular version in the full interval, just get the whole taste of things here. We're going to go 2 units below, hit it there, 2 units above, so we got a maximum height of 3. And here's what the rectangular curve should look like. If I translate that over to a polar curve, now, I want to start right here at pi over 2, which is going to put me at -1. And then I exit the inner loop right there at, I believe that's 5 pi over 6. So we entered the loop at pi over 6, and then we exited the inner loop at 5 pi over 6. At pi, I'm 1, and then at 3 pi over 2, I'm way down here at 3. We'll put a 2 in the middle there. So here's what we did. So that's what that limicon looks like if I start at pi over 2 and then I go all the way to 3 pi over 2. In fact, I wouldn't be afraid to maybe, let's see, I'm going to put a label. That's where pi over 2 is. That's where pi is. And then over here, this is where 3 pi over 2 is. Okay? And right there, that pole, that is 5 pi over 6. I think it's very important to keep track of the order that you plot the points in and the path that you take as you plot them sequentially. All right, so that's all they wanted me to do in part A. Now, as far as part B goes, they said let S be the shaded region in the second quadrant bounded by the curve and the x-axis. So let's go ahead and we'll actually shade that in a little bit. Let's say that this is what they're referring to with region S. And they want me to find the area of S. So that's not too bad. We've memorized our area formula. We're feeling pretty good about that. We know that it's going to be 1/2 the integral from, now the bounds. That region starts at 5 pi over 6, and it ends at pi, and then the curve is simply 1 minus 2 sine of theta. We'll wrap it up, we'll square it, we'll throw our d theta on there, and that right there represents the total area of that little shaded region. Okay, so we got part B done. That was a piece of cake. Now for part C. This is the big bear. The next thing they want you to do is we're going to sketch r equals negative cosine of theta. Negative cosine of theta. So we've got a circle, but usually it's symmetric with respect to the x-axis in the first and fourth quadrant. The negative is going to flip it over the y-axis and now put it in the second and third quadrants. Again, why don't we take our time and see if we can't sketch negative cosine, rectangularly speaking here. Negative cosine would look like, it would start here, it would curl up, hit that, and then it would curl down. So what happens is, if I want to plot this on the same graph, and I'm use some blue, when they say 0 degrees or 0 radians, the r value is -1. So the very first dot you put is going to start right there. Then you're gonna move this way until you hit pi. Now, how did you know to go underneath the x-axis and not above it? Well, the reason here is right here. Let's say you wanted to plot pi over 6, comma, negative radical 3 over 2. The negative r value is pushing you down into the third quadrant, and in fact, I think it's going to get a little deeper there, and it's going to shoot up and above. So, and again, remember, it only took pi radians to complete that entire circle. And that circle, the blue one, definitely goes above the limicon because the limicon just barely creeps above the x-axis. Now, what they want us to do is they want us to find the area that lies in between those two And this is going to be a very challenge. So I'm kind of visualizing this area right there that I want to try to find. First thing I'm going to do is I'm going to set up two integrals. I'm going to do one integral that represents all the area inside the blue circle that's above the x-axis, and then I'm going to do one that represents everything inside that limicon, which is actually what we did earlier in part B. So, oh boy, how are we going to set up this integral? The first, let's do 1/2. Now that circle is going to, let's see, right there is pi over 2 on the circle. And then we're going to, let me highlight this. This right here is pi over 2, and then we're going to rotate until we hit pi. Got that? Starting at pi over 2, rotate until we hit pi. So here's what this looks like. Start at pi over 2, go until we hit pi. We've got the curve negative cosine of theta, let's see, squared, d theta, and then minus everything that you just did in part B, which would be 1/2 the integral from 5 pi over 6 to pi, 1 minus 2 sine of theta squared. And that, ladies and gentlemen, is going to be the area that's in between those two. It's basically the area that's inside the circle but outside of the limicon. Now, by far, the most trickiest part about this one is the fact that the two curves appear to intersect right there at the pole, but they're passing through the pole at different times, okay? The limicon doesn't hit that pole until 5 pi over 6, whereas the circle hits it at pi over 2. So it's kind of a false intersection point in the sense that, yes, they do go through the same point, but they go through that point at different times, and so they don't actually collide. Collide is a word we're going to start to use more and more when we get into parametrics with, all right, were they at the same location at the same time, or were they at the same location at different times? All right, let's get one more example here under belt. I want you to consider the curve r equals 3 plus 2 sine of theta. Now, what are your expectations right there? Is this a cardioid? Is it a limicon with an inner loop, or is it a limicon with a dimple? Hopefully you said it's a limicon with that dimple in it. And the dimple is going to be real nice, smooth, and differentiable. That's the big difference. The cardioid's non-differentiable when it hits the pole, but our dimple is going to be nice and smooth throughout the entire curve. And I also want you to consider r equals 2, which is a very well-behaved circle that's centered at the origin or at the pole with a radius of 2 going all the way around it. So we're going to try to sketch both of these curves, and then we'll try to find the area that happens to be inside both of the curves. And let's see, I think this is a good one to do rectangularly. Let's see, we got pi over 2, pi, 3 pi over 2, 2 pi. We've got a vertical shift up here at 3. And then we're going to go, we got an amplitude of 2, so we're going to go 2 units above it. And then we're going to go 2 units below the 3. So we've got a maximum height of 5 and then a minimum height of 1. And let's see what this looks like here. I'm going to maybe go down here now that we've got that drawn. I'm going to try to come up with one real nice big graph. All right, let's go. Do I have enough room to go up 5 units? That's the key. 1, 2, 3, 4, 5. We'll say there's 5. 1, 2, 3. 1, 2, 3. I think we just need to go down 2. All right, so here's what that limicon. It's going to start at 3. It's going to go up and hit 5. It's then going to hit 3. Then it's going to hit 1, and that's where that nice little wrinkle or wave comes from. And a little nervous about this one. These ones usually come out a little scary. We got to go below that point, come up, wrinkle, go below it. Not too bad. One of my better ones. One of my better ones. All right, then the next curve, I just want to draw a nice circle with a radius of 2. Easier said than done. Let's see what this is going to look like. We're going to swoop around. All right. Now, so what we're doing is we're see where the two graphs overlap with each other, and we want to find the area that's inside of both of them. And so basically what I'm going to do is I'm going to try to visualize the radial lines. I always want to start here at 0 radians, and what I'm going to do is I'm going to rotate counterclockwise. We've got that wiper blade moving. There's pi over, we hit pi over 2 right there. Still bounded by the circle. All right, let's see, there's 3 pi over 4, yada, yada, yada. We're moving. There's pi, and we're continuously moving, and then all of a sudden, boom, right there's the magical intersection point. Let's call that, we'll call that alpha for right now. And so what that means is I now have to stop and set up a new integral. And what I'll do is I'll switch colors to green here maybe. So then from alpha, I'm bounded by the limicon, the black graph, until I hit this magical point right there, boom. That intersection point, let's call that a beta. And then from beta, moving forward, I'm going to start to be bounded by that circle again until I hit 2 pi. So really right now what I'm thinking is I'm going to need 3 separate integrals. We're going to go from 0 to alpha, then we're going to go from alpha to beta, and then we're going to go from beta to 2 pi. So the sum of those 3 integrals is going to represent the total area that's inside of these rascals. And of course, and certainly you could make the argument there is a more concise way to do it. You can do it in 2 integrals or 1 integral, but I'd like to start off with these 3 integrals because I think it makes the most sense visually here. All right. So as far as, let's start with red. Okay, we're going to go 1/2 integral from 0 to blank, whatever the intersection is, of r equals 2 squared. All right. Now the question is, where do they intersect with each other? So how do we get that intersection point? Well, let's go ahead and set the 2 curves equal to each other. 3 plus 2 sine of theta. When does that equal 2? Let's subtract that 3 over. Let's see here. Gives us -1. And then when does the sine of theta equal -1/2? Well, let's see, reference angle's pi over 6, so I'm thinking, let's see, what does that need to be? 7 pi over 6 right there. And then the beta is going to be 11 pi over 6. Okay, so the first integral is going to go from 0 to 7 pi over 6. Let's switch colors. Let's go to green. Okay, the green area, let's go 1/2 integral from 7 pi over 6 to 11 pi over 6. And that's going to be, let's see, 3 plus 2 sine of theta squared. And then last but not least, let's go get that purple region. I may drop down here. Let's go 1/2. Let's go from 11 pi over 6 to 2 pi. And then we're back to being enclosed by that blue circle, so we'll just say 2 squared d theta. All right. So the sum of those 3 would give me my total combined area that's inside those both. Now, we've mentioned that there's a more concise way to go about this. In fact, is it even possible to just do it with 1 integral? Well, I might have been too ambitious. I don't know if it is possible. But for instance, let me challenge you with this thought, and we'll kind of make this extra credit. Can you condense this integral and the purple one so that it's just 1 integral? Okay, can we find the sum of those, the red and the purple one, in just 1 integral? The other shortcut we could do with the green one is, instead of from 7 pi over 6 to 11 pi over 6, we could change the upper bound to 3 pi over 2, which would be the halfway point, and then double the answer, which would then kill that coefficient. But again, let's throw that out there for extra credit. Let's make it we'll make it a few extra points on your next quiz. How can we combine the red and the purple one into 1 integral? So good luck. We'll see you tomorrow.